Okay, so the topic of today is going to be a canonical ensemble. If you remember, we solved several questions about microcanonical ensemble, and it's time to move on. Okay, so how we define different canonical ensembles. Okay, so how we define ensembles and what are the meaning of ensembles at all. If you remember, we had this ergodic hypothesis, right? That the temporal average and the ensemble average are exactly the same, okay? Or we assume that they are the same, so we can compute this value. And what is this value is? It is a sum over all possible states of the system. We have Fi is the probability for the system to be in state I multiplied by Ei, which is the energy of the state. Now, this applies when our observable is energy, but in general, any observable O, right? It can be the magnetic field or induction. It can be the pressure. It can be the length. Whatever your favorable observable is, okay, O stands for observable. So the average O is always a sum over I, Fi, Ei. Great. So we need OI. So we need two assumptions or ways, whatever you call it. First, in order to define what are Fi, and the second is what are the energies. Now the energies or observables, they're coming from the model. If you remember, we had an Einstein model, we have a two-state model. You have additional examples during the TA. So this depends on the situation. Fi, so previously for the microcanonical ensemble, we assumed something. We said, well, all the probabilities are the same. So we had a uniform distribution over all the different states. Right? This is probably the easiest and the most basic distribution that you can think of. And this is the way microcanonical ensemble works. Right? It assumes that everything is uniform. Now we are trying to make one step forward and to make things a little bit more complicated. Okay? So if for microcanonical ensemble, Fi uniform. Now, what is the distribution or probability that is still simple, but it's on the level of the uniform distribution? Okay, let's go backwards in time to the time when you were maybe I was teaching or somebody else was teaching you probability. So we start with uniform, and the next thing what we do? No, so that much more simple. No, even simpler than that. So there is a probability and there is a conditional probability, right? There is something which is called conditional probability. Okay? What is a conditional probability? If you have a sample space, okay? If you have a sample space, and this was omega, right? Conditional probability basically meaning, well, I know that B happened. Okay, what is B? Something that occurred. Basically taking your whole space and saying, my sample space is not omega anymore, it's subspace, let's call it B. Right? So instead of calculating P of A, I'm going to calculate P of A given B. Canonical ensemble. F of I is uniform, conditional probability. Okay. So what are the examples that usually are used in order to define conditional uniform probability? let's think about the simplest example of a dice. I'm rolling a dice, so 2 cubes with numbers. Okay. Back to probability 101. Okay. And I'm looking on my sample space. Okay, so this is cube number 1, and this is cube number 2. Okay. And cube number 1 can obtain values of 1 and 2 and 3 and 4 and 5 and 6. And cube number, this was 2, this is 1, can also obtain values of 1 and 2 and 3 and 4 and 5. And this two-dimensional space, right, okay, look like this. And this is 6. Are the all different values that I can obtain in my experiment. Okay, so my experiment, how I define probability in the first place, I say I have an experiment. So my experiment, I am rolling a dice and I'm looking on the outcome. The first dice can show me 1 up to 6. The second can also show me 1 up to 6. Okay, so all the squares here, it basically says what are the different outcomes of my experiment. Right? So for example, this square over here is an outcome 3, 3, and this one is 4, 4, and this one is 6, 1. Okay? So this is 6, 1, this is 3, 3, and this is 4, 4. Uniform distribution. What is a uniform distribution? Uniform distribution tells me that the probability of each of those squares of any outcome is exactly the same, independent of the specific value that this square represents. What is a conditional uniform distribution? Conditional uniform distribution, for example, I'm telling you, well, the sum, okay, the sum of those two values equals exactly to 3, 4, okay? Let's assume that my condition is that I'm rolling my dice, okay, and I know that the outcome of the first cube plus the second cube is in total 4. Okay, so what are the probable outcomes? So 3, 1, this is good, right? What else? 2, 2, and 3, 1 over here. So if beforehand my sample space was all the total amount of all those squares that I just plotted over here, if I'm conditioning on the outcome and I'm saying the condition is that the sum of the result of the first and the second is 4, so my subspace, instead of all this, becomes 3 different squares. And then I ask you the following. So how the probability is defined when I'm looking on uniform conditional probability. Okay? So what is P A given B? P A divided by P of B. And if we are dealing with uniform conditional probability, so it's the number of events in the group of A cross B divided by the number of events in B. Alright? And that's it. So the whole difference between the canonical ensemble and the microcanonical ensemble is that I am assuming or I'm conditioning on the outcome. Okay? So what physically I'm actually doing. So what is the physics? So this is something about mathematics. The physics is very simple. Microcanonical ensemble, the system was closed. It has no interaction with the outside world. This is microcanonical ensemble. So this was my system. Okay? And everything outside have never affected whatever is going on inside. Okay? This is a microcanonical world. Canonical world, we're saying, well, our small system, well, it's actually macroscopically small, is a part of a big system. Okay? And it can exchange energy with the system that it is part of. So this is called a heat bath, or sometimes reservoir, right? And this heat bath, together with our system, it is a closed system. Okay, so this heat bath cannot exchange energy or particles or anything with the outside world. Okay, so this is some sort of a conditioning, right? This is the conditioning. We condition that what? The total system is a closed system. But our system is now a part of this closed system, and it can exchange energies with this heat bath. And that's it. Right? I do not assume for the canonical ensemble that it gets exchange particles. It only can exchange energies. And I'm using this definition of the number of states in A cross B divided by the total number of states in order to define what are my different probabilities.
So we assume that the probability for each state is the same.
We assume that it's a conditional.
Under B here.
Yep, exactly. So Fi is as follows. The number of HB the number of states of heat bath where the total energy is E total minus EI divided by the total number E total. Okay. So what is my condition? I know that the total number of states or the total energy is constant. Okay. And I'm assuming that my system has an energy EI. Okay. That it means that the reservoir has the energy of E total minus EI. Okay. So I'm saying what are the different numbers of states that I have is the different number of states that the heat baths have under the condition that the total energy is E total divided by the total number of states of the whole system.
I think it's supposed to be just EI.
Sorry?
You said that E total minus EI.
Because what is the energy of here? Of the heat bath, not my energy. This is my system. Okay, this is my system. And this is the heat bath. So if the energy of my system is EI, the energy of the heat bath is E total minus EI. Okay, why? Because the total energy is constant.
I understand why this is the energy. I just don't understand why you put the E total minus EI and not just EI.
Because the heat bath is energy is what?
E total minus EI.
Yeah. So it's good.
But you wanted the probability of our system,
So-
not our heat bath.
But I cannot start until, well, it's a good point. It's a good point. And I need some sort of an assumption that you will see in a second about the heat bath. And this assumption is going to be introduced during the concept of temperature. I'm going to expand this guy in a Taylor series, right? And I'm going to say the temperature or the second derivative of this guy with respect to something is going to be constant. This is the temperature. I'm going to use something additional. I'm going to use that the temperature is constant.
So the Fi that we found is not probability for our system, it's probability for the heat bath.
No, it's the same. It's the same, right? Because if it's the same, because if energy is what defines the state, right? So there is a specific state. If I have EI, this has exactly E total minus EI. Okay. It cannot be that, well, this is the whole point of this. The moment that I say my energy is EI, okay, I know exactly what's the energy of the heat bath. But for the heat bath, I'm also saying that it's so large that its temperature is constant. And we're going to see this in a second. Everywhere. Everywhere. Because we assume that EI, so we assume the temperature of our small system and the temperature of the big system is exactly the same. We assume that they are in equilibrium. Again, this is a class about equilibrium. So if this, our system, is in equilibrium with the heat bath, their temperature has to be exactly the same. Okay. Yes?
Why don't we count the states of the system? Why do we count the number of states of the heat bath?
We can, and it's going to be exactly the same. It's just the streak of saying my temperature is constant. It's easier to assume that this is a macroscopical system. And we will see forward in the class that actually my system can be microscopical. And it's hard to say something about the temperature of microscopical system. This is why I assume to talk about this system.
So
it's better to talk about temperatures of large systems and not of small systems.
Mm-hmm.
Right?
Do we get the same?
You will get exactly the same result. Even more, I will introduce the way of defining what is an entropy, Shannon entropy, and then it's completely unimportant. Right?
סטאס, אנחנו רואים שכל הזה שלנו בסך הכל מבודד לחלוטין.
Yes. So everything, the heat bath and the system is together form a closed system that does not exchange anything with the outside world.
ולמה קראנו לזה FI? יש סיבה?
This is a historic why it's called a heat bath or zero. Alright. So what we are going to do, we are going to represent this by what? By using the entropy. Okay. So S total it's K Boltzmann log of omega total. Right? And S of heat bath is K Boltzmann log of omega heat bath. Okay. Those are the standard definitions of how the number of states relate to the entropy of the system.
But haven't you said that this definition of the entropy is only true for microeconomical examples?
Exactly. So what I'm trying to do here, I'm trying to say this system is extremely large. Okay, the system is extremely large, so I'm assuming that its entropy can be described and those exchanges of the energies are small. That way, I'm assuming that its entropy is defined as if it's almost a microcanonical example. Okay. Now, when I'm trying to do it that way, those assumptions are needed. We will see that actually there is an alternative representation, more mathematical, more general, when you do not need to assume anything like this. Okay. So we need S total. Of what? Of E total. So we are going to have here omega total of E total. And here we need S of A heat bath of E total minus EI. So here I'm going to introduce heat bath of E total minus EI. So let's first treat. This is the first term, this is the second term. Now, I'm assuming the following thing. Let's take this S total and separate it into two systems. If we assume that the energy, everything is macroscopical, so this is the playground. I assume that it's big enough, right? But it's also, this is not too small. So I'm saying that S total, so this is for 1, that S total E total can be described, okay, by S of system of some U, where U, I'm assuming the average energy, okay, plus S H bar, oh, heat bath of E total minus U.
You're thinking quantum
I know. I heard a lecture about quantum mechanics half an hour ago, so I'm still in the quantum world. Okay. Why can I do this step? Why can I do this step?
Okay, good extensive.
Entropy is extensive property, has an extensive property. So as the entropy of two systems, okay, it's just the sum of the entropies. So if I'm assuming that the energy of my system, let's for a specific instance, we will say that my energy was U, where U I'm saying U is average energy of the system. Okay. Due to this extensive property, I can make this step. Okay. So this is one, right? So instead of writing it like this, I'm going to represent it like this. Okay. The next step is somehow, okay, somehow to take S total and represent it in terms of U and E total minus U. Okay. So this is the second term. So the second term, I have S heat bath equals to of E total minus EI. I simply will write it down as the entropy of heat bath, E total minus U, right? Because here I have E total minus U. But I cannot simply introduce here E total minus U. I will have to subtract it, so I have plus U minus EI. And that's it.
What's the difference between U and EI?
EI is a specific energy of a specific state. U is some average energy that I don't really know what it is, but I introduce it over here.
It's an average energy of what?
Of my system.
Ensemble average, not time average, right?
I'm talking about ensemble average, yes. So it's a, let's assume that I have, what is U? Okay, so what is U? What is U? U, if U is E average of my system, which is a sum over I, Fi, EI.
EI is the energy of each particle?
EI is the energy of each state of my system. Remember, my system have different states. I assume that each state has a specific energy, and in order to compute the average energy, I need to perform this operation. Other questions? Okay, so what I do with this, I expand it in a Taylor series. Now this is heat bath of E total minus U. Why I did that? Because here I have S of heat bath E total minus U, right? But I have also additional terms. What my additional terms are? Plus ds to dE, okay, ds to dE, multiplied by U minus EI, plus 1/2 of d squared S to dE squared, multiplied by U minus EI squared, plus etc, 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 etc. So in order to represent this correctly, I need to take the full Taylor expansion, and it's actually hard, but here I do a trick. What is the trick? What is ds to dE? My temperature, right? 1 over temperature. So here I have 1 over temperature. What is this guy? Yeah, no. This is derivative. The derivative, and the temperature is constant. Okay, so it's 0. Okay, this is why I needed an assumption that my temperature is constant. And what happens to everything what I have here? I don't care, because I assume that the temperature is constant. And the moment the temperature is constant, only this deviation from E total minus U is important. Everything else is not. Okay, so we arrived to the following result. So one was this. And the second representation is that S of heat bath equals to S of heat bath at E total minus I, E total minus EI, equals to S of heat bath of E total minus U plus 1 over T U minus EI. It's actually not bad because you see we already have the probabilities are related to the number of states. The numbers of states related to the entropies. And the entropies are somehow related to each other. Right? So we have S of the system, S of the heat bath, okay? And here we have S of the heat bath and 1 total. So I completely forget now that actually I'm treating a closed system. I'm only looking at what happens in my system on the average, okay? And I also care about the entropy of the heat bath, which is extremely large. So now it's the time to put everything backwards into this equation.
Stas, I have a question with that.
10.
At what point we make the expansion Taylor?
So we at what point what? We neglect all of this?
No.
For this guy, for the second guy. You see? This guy. So I'm looking at what is the entropy of the heat bath, and I don't want it to be represented in E total minus EI. I want to insert inside this.
In terms of U.
שאר הגורמים בטור טיילור שם, בפיתוח של השני, פסלו בגלל שהטמפרטורה הייתה קבועה?
Yes.
או בגלל שפשוט לא רוצים להזניח סתרים קבועים?
No. We assume that the temperature is constant, so everything else is exactly 0. Okay, so what is Fi? Okay, so we have E, right? So what terms goes over here? This one, right? So it is E, let's write it slowly, of S heat bath of E total minus EI 1 over K Boltzmann divided by E of 1 over K Boltzmann of S, this is total, right? S total of what? Of E total. Great. Next step, we write down what is exactly S of heat bath in what terms? In those terms. So it's 1 over K Boltzmann of S heat bath E total minus EI plus 1 over T U minus EI minus U, thank you. Okay. Divided by E of 1 over K Boltzmann. S total is SU plus S heat bath of E total minus U. So here we have S heat bath E total minus U plus S of system of U. Okay, so what terms are getting neglected or just cancel out? This and that. Okay, so what we are left with is E 2 T or 1 over K Boltzmann T. Here we have U minus T of S of U. Okay, this is an S system. Multiplied by E to the power 1 over K Boltzmann T EI. Alright? Now this looks nice, and I'm going to say that 1 over K Boltzmann T is beta, okay? And S system of U, okay, it's simply entropy S of my system, okay? And look, eventually everything that was related to the heat bath, to the total system, to the number of states, everything disappeared, right? We are left with purely thermodynamical quantities. What is this guy over here? Right. So we have E of beta multiplied by F, which is the Helmholtz free energy, multiplied by e to the minus beta EI. This is Fi. Okay. Now, what do I know? I also know that a sum over I, Fi, equals to what? 1. Because this is the probability to be in state I. This is the total probability being anywhere. And the total probability being anywhere has to sum up to 1. So this is equals to 1. Okay. So what we are getting? We're getting that e to the beta f sum over I, e to the minus beta ei equals 1. Okay. Let's take this part out of the sum. So we have a sum over I, e to the minus beta ei equals 1. And here we have e to the beta f. Okay. And I want to just write it as a sum over I, e minus beta ei equals to e to the minus beta f. This sum over I, e minus beta ei.
What is beta?
What is what? Big F. Helmholtz free energy. Okay. This is Z. This is called a partition function. Okay. It's completely defined by the microstates of the system. Okay, in our assumption of canonical ensemble, which are defined by the energies of the system, and the energies completely define the probabilities. Okay? So this is Z. We know that Fi equals to E minus beta ei, and we know that F, which is the thermodynamic quantity that we can relate to observables, but average observables, equals to what? It equals to minus 1 over beta log of Z.
If I don't, we need to multiply it by E.
Well, this comes from here. Z equals to e to minus beta f. This means that log of Z equals to e to minus by beta f. This means that beta equals to 1 over beta, so f equals to 1 over beta log of Z. Oh, okay, okay, yeah, you are absolutely right. I forgot this part. Thanks. So this is the probability, right? So this is the probability. Fi equals to e to the beta f. Fi then means what? E to the beta f we write as what? As 1 over z. 1 over z e to the minus beta ei. Okay. Or, okay, I'll make it slower. From here we see that Fi equals to e to the beta f, right? E minus beta ei. I know that z equals to e to the minus beta f. So I substituted it inside and I obtained that this 1 over z e to the minus beta ei. Okay? And this is the central formula of statistical mechanics, at least when we are talking about canonical ensembles. All the probabilities are completely defined by the temperature and the energies of the different states. How I obtain the different energies of the different states? Give me a model and I'll find you the energies and I will find you the different states. I cannot say what are the all possible states and what are the all possible energies of the system. I don't know that. But for any model, simple enough, usually I can find those things. So the task becomes, you're providing, or somebody provide us a model, and we try to understand what is going on inside the system by using the structure of statistical mechanics and canonical ensemble. Because now we have an exact formula of how to compute different probabilities. The moment we have probabilities, we can obtain anything that we want. Absolutely anything. How do we relate this? Okay? How do we relate this to thermodynamics? Remember, because in real life I measure some thermodynamical quantities. How do I relate it to thermodynamics, to the second law of thermodynamics, and all the stuff that we have learned from this equation? Okay? So F equals minus 1 over beta log of Z enables for me to obtain the Helmholtz free energy, and the moment that I know the Helmholtz free energy, I know what the pressure is. I know what the chemical potential is. Whatever I like, I can obtain by taking different derivatives of F. Okay, so the structure is, if I'm working in canonical ensemble, I know immediately that the different probabilities are provided by this formula. All that I need to find are the different energies of my system. Okay? And the moment that I know the energies of my system, I can compute the partition function. And the moment that I know the partition function, I know this guy. Yes, I have to know I need to know something, right? I need to solve, eventually I need to solve something. I cannot know everything. But yes, so the whole problem was, there are two problems. A is to compute the different energies. B is actually to compute this partition function. It's usually hard. Okay? So we need actually simple enough models for which we can solve and obtain something. Now, is it at some point I said the following thing. We assume that U is the average energy of the system, right? This is what we assume. Now, I computed exactly what are the different probabilities. So, I should obtain that U equals exactly to what? Okay. By definition, it has to be equal to what? To a sum Fi EI, right? This has to be satisfied. So if everything that I've done is correct, I can now go, forget about U, use only this formula, compute the average energy by using this formula, relate it to the free energy somehow, and obtain U. Because I know that U is related to the free energy by using this formula. Free energy is U minus Ts. Okay. So let's do this. Let's check if it actually works. So what is the sum of I, Fi EI? Equals to sum of I, EI, and instead of Fi, I'm writing this formula over here. 1 over Z, e to the power minus beta EI. I can take this Z out, right? And have 1 over Z, a sum of I, EI minus E minus beta EI. Okay. What do we next? How we compute the sum? Z, we don't care. What? Exactly. How this trick is called? The Feynman trick. This is the Feynman trick. Yes. Well, you haven't studied probability. So this is the Feynman trick. Have you seen this Big Bang Theory series? Yes, so there, this guy solves something with the Feynman trick. So if they know how to solve, you also should know how to solve it. It's basically looking on this saying, oh, this is just a derivative with respect to some parameter. So that equals to 1 over Z, a sum, and I'm looking on this and I'm saying, well, if I take the derivative with respect of beta, right, of e to the minus beta EI, okay, what the derivative with respect to beta actually does, it removes minus EI downwards. Okay, so I can say that this is minus d to d beta e to the power e minus beta ei. Because if I perform this derivative, what gets down from the exponent? Ei with the sign minus. So minus minus will give us plus. And I will left with ei multiplied by e to the power minus bi. Now, we can say, well, all of this converges. Okay, so we uniformly converges and whatever. So we can take this derivative outside of the sum. So this is 1 over z minus d to d beta of what? Of a sum over I, e minus beta ei. Okay. Now, what is this? Z. So we have 1 over z minus d to d beta of z. What is this? Minus d1 z d beta. Okay, so this is minus d to d beta of log of z. Okay, so we know that u is provided by this formula, or must be provided by this formula. But log of z is already something nice, right? Because what is log of z? Minus beta f. Okay. So in order to actually achieve something, right, what we need to do, we need to take this and show that if we put inside of log of z beta f over here, okay, we eventually come to the fact that u equals to u. Okay, let's see. What is minus d to d beta of minus beta of f? Okay. It equals to what? It equals to minus minus, so this is d to d beta of beta f, which is f plus d f to d beta multiplied by beta. Okay. Now instead of using beta and etc., I can say, well, let's substitute here 1 over k beta t, right? So this is f plus 1 over k beta t d f to d 1 over k beta t.
Wait, that's it.
What?
You said that t is constant, so beta also is supposed to be constant. So how?
Of course, but I take a derivative with respect of t.
Yeah, but you said t is constant.
I'm not taking derivative of t. I'm taking the derivative with respect to t. T is a parameter.
T is also constant.
So, I don't understand the question.
Beta is constant,
Beta is a parameter of my system. I can change it.
but it's a constant.
No, I can change it.
But you said t is constant.
Okay, so you, all right. I set t, and then I look on the equilibrium, all right, and I'm obtaining everything with respect to parameter t. And now I can go and change my parameter t, and look again on the new equilibrium that is going to be created. Okay. So t is not a function that is changing. T is something that I set, and I look what's going on inside the system for a specific value of t. But I can also look at what's going on to the function or different values in the system when I'm going to change my t. Okay? So t is a parameter. For me, it's a parameter. And it's every time that I look on the system, it's set to be constant. Okay? Okay. So what is going over here? What is df to d1 over k Boltzmann t? So we can take k Boltzmann out. See, we have k Boltzmann over here, we have k Boltzmann over here. They are not parameters, we're not modifying them. So k Boltzmann disappears. We have here d of 1 over t. This is simply what? D of f to 1 over t squared minus dt. Okay? So I have what I have inside. I have F minus 1 over T squared, 1 over T, multiplied by T squared, dF to dt. So what we obtain? We obtain that minus d to d beta of log of z equals to f minus 1 over minus t df to dt. What is df to dt? S. How do I remember this? df equals to minus s dt plus minus pv. pdv. Plus? No, this is okay. This is good. This is good. Okay, so all of this equals to f plus ds.
You will give us the formulas in the equation.
Never.
Never?
Plus u. No, I'll give you something like this.
Okay.
Okay? So you see what we arrived. We started that we have a definition of u. We arrived to this guy. Now we use some additional thermodynamics, and it indeed equals u. Okay? What it means that all our assumptions and all our methods that we use so far are self-consistent. Right? I assume that there is some energy, average energy u. I pushed it inside as a parameter. I have no idea what u is. Remember, I have an entropy of my system, and there is some average energy u. What is exactly u? I don't know. I don't care. Right? There is some u. We worked out, we computed the probabilities, we obtained a formula for the probabilities, right? What was the formula? This was the formula for probabilities. We computed the partition function, okay? This was the formula. And then I said, let's check if our assumption about the average energy was correct. And this is indeed what happens, right? Our average energy is minus d to the beta of log of z. This is a microscopic quantity that assumes some knowledge about the specific energies of the system, right? And we obtain that it exactly provides us that it equals to the thermodynamic u that we used. Okay? So everything is self-consistent. Everything is self-consistent over here. Alright, so now that we sure about our self-consistency, we can move forward to solving something. Yes?
Question.
Yes.
The definition of Z, is it correct just for discrete systems or also for...
We will get to this question when we're going to talk about continuous spectrum of energies.
Okay.
Right? So for continuous spectrum of energies, there's going to be an integral instead of a sum, and some specific an additional function, which is a density of energies. Okay? This now so far is a discrete representation for discrete spectrum of energies. How we use all of this? All right, so great. This is nice. Self-consistency. How do we use this in order to solve problems? What do I know how to use to solve? Questions?
כן, כן, שאלה קצרה.
Yes.
אנחנו הגדרנו אבל את הדיפרנציאל של F, על ידי זה שהגדרנו במקור את F להיות E פלוס DS, TDS, TS, ואז אמרנו מה הדיפרנציאל של DF. אבל פה אנחנו שמנו את הקשר הזה, לא בשלב?
No. We made sure that everything is self-consistent. We assume that we have an average energy, and we prove that this is an actual average energy thermodynamical.
אז איך יכולנו להשתמש פה בדיפרנציאל הזה שפה?
What?
איך יכולנו להשתמש בדיפרנציאל הזה?
This is a thermodynamical assumption.
התחלנו עם זה.
No.
לא השתמשנו בו, פשוט אמר זה הדיפרנציאל.
No, that's it. This is a thermodynamical knowledge. I don't want to prove it. I want to start with microscopics and arrive to macroscopics. And I did this.
זאת אומרת, אתה לוקח שאנרגיה UI...
You're repeating yourself. Okay, so how to use it? How to use this formalism? Okay, now, as always, we start with something extremely simple, and this is a gas of particles which are not interacting, and then we are going to complicate things. Okay. So there are two specific assumptions that we need to take into account in solving any problem. One, additivity of energy. And number 2, factorizations. I will explain both those terms. So additivity of energy is very simple. Okay? חיבוריות של אנרגיה, פקטוריזציה. כפילות. Okay. I will explain this in English, what exactly it means. So additivity of energy is simple. I assume that the total energy, so what is additivity? The total energy is the sum of all energies of the different particles. Different particles of the system. Not exactly, and I will show why. And this is why I'm saying particles in parentheses. It's not exactly extensivity. First of all, because I'm talking about microscopical particles and not macroscopical system. Okay. And extensivity applies only to macroscopical quantities, not microscopical particles, because particles can have interactions. Okay, this is one. B, I'm using particles in parentheses. We will show, or I will show to you, that in order to solve any problem, sometimes we cannot use what you meant by extensivity, and we need to turn ourselves into description of particles which is not so comfortable to us. Okay? We will see what particles, each time we will have to define new particles. Particles is not always those small balls with masses or whatever. Particles sometimes are going to be groups of particles, or specific waves, or specific interactions, or specific degrees of freedom. Okay? Those are the different particles, and we want to use different representations for different systems. So this is additivity, and we need this. Okay, I will show you to you why.
You said extensivity is right only for macroscopic?
It's like extensivity for macroscopical system, yes. But I'm talking here about particles, and particles are microscopical.
Okay.
Okay? So what is factorization? Let's see. So let's assume that my total energy in a state EI, and I have many particles in my system, many degrees of freedom. And I'm assuming that I do have this additivity, so the total energy is equals to epsilon 1. EI is what? Is the energy of the system when the system is in state I. This is epsilon 1I plus epsilon 2I plus epsilon 3I plus epsilon 4I plus etc. 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 Why?
שלא יהיה בריבוע כאלה.
לא, אנחנו מדברים על EI, לא? אנחנו מדברים ב-E1, יש לנו אפסילון 1, נגיד, ואפסילון 1, 2, ועוד אפסילון 1.
So you want this as subscript and this is subscript, this is the subscript and superscript. Okay, but this is the total energy, and this is the energy of single particle. It actually doesn't matter when you put the symbol, the index. Okay, so this, what is this? This number here, epsilon, this is the number of the particle. What is I? This is the state. The state of the whole system. our system. You're absolutely right. Of our system. So if I want to compute, what I need to compute, I want to compute the partition function is a sum over I, okay, sum over I, e to the minus ei. We know, okay, now, those EIs over here, remember, they define a specific state. Okay? They define a specific state. Now, I want to represent this whole energy a little bit different. I'm saying, well, this epsilon, okay, J is the number of particle, and I over here is going to be the different self-energy of my macroscopical particle. So if beforehand I'm saying, well, this is a specific state, right? This is a specific state, and here I are the states, and this is a natural description. But what was going to happen if I'm going to change only the energy of this first particle? It's going to be a different state, right? So all the states are described not by one single number that stands over here, but many numbers. So I want to say that I over here, let's call it K, the state, or the self-state of the particle J. So what do I need to sum over here? So if I'm looking on this as a self-state, the total energy is still described by those guys, but my running index is already not I, right? I need to run over all Kj, over all Kj, K1 and K2 and K3 and K4 and etc. of e to the power minus beta. And here I have epsilon 1 K1 plus epsilon 2 K2 plus epsilon 3 K3 plus epsilon 4 K4 plus etc.
All the cases equal to I.
Not exactly. So here I said let's put here one single index in this total energy, and this index is going to represent a specific energy of the first particle, a specific energy of the second particle, a specific energy of the third particle, and etc. Now let's turn this upside down. I'm saying let's look on a specific energy of the first particle, completely different energy of the second, a total different energy of the third and the fourth. Okay? And by using a specific indexation here for the first, a specific indexation for the second, a specific indexation for the third, represent the total state with those numbers of K1 and K2 and K3 and K4. A specific set of K1, K2, K3, K4 represent a specific state 1. Another specific state of K1, K2, K3, K4 represents state 2. And etc. So instead of going over all different states of the total system, I'm going over all the different states of the single particles in my system. Okay?
But Stas, then you have to sum them too, right?
Yeah. I sum over all the different K1, K2, K3, K4s here. You see? I sum, instead of summing over one single index, I'm summing over everybody. Okay? You're right.
So isn't the interaction between the particles included in the potential energy of them?
Oh. So this is a fantastic question. So what is that this guy cannot be in a specific state without affecting this guy, turning it also in a very specific state, like entanglement in quantum mechanics, right? Okay, so this is, if this is spin up, this has to be spin down, or something like this. Right? This is called correlation. So most of the physical systems, this correlation is very important. So I cannot simply sum over all the different K1, K2, K3, K4. I have to take into account all the different constraints.
But additivity is when the particles are...
No, additivity is this guy. Additivity is only this. Right? What she's telling us is something different. Additivity, that I can write this as a sum. Now what she's referring to is that I cannot simply sum up over the different indices, because when this is in state 1, this has to be in state 2. It cannot be in state 3. Okay? This is called a correlation between the different particles. They affecting each other. The moment they are affecting each other, what it means that if I'm standing down, there must be a floor beneath me. Right? So this is a very strong constraint. I cannot stand in air. So this is somehow my energy here affects something else. Yes.
אבל בטח הצטרפתי בסכימה בשביל הקורלציה, אבל בטח האינדקס של אפסילון 2 לא תלוי מכ-1.
Why not?
בצורה שכתבנו.
No, but you cannot say, what I'm saying is the following. If K1 equals 1, it leads that K2 equals 3, has to be. I cannot simply say, well, K1 is 1, K2 can be whatever number I like. It can't.
יש לי הרבה אפשרויות שאני חוזרת עליהם כמה פעמים בסכימה.
No, or this is easy. The problem is that there are forbidden states. Okay, there is no state where K1 equals 1 and K2 equals 2. It's forbidden. This is a sort of interaction. I cannot simply sum over everything. Right? You can say, oh, Stas, I here have, if I have n particles, I have n sums over here. What I'm trying to say to you that in most systems, this is not the case. Because some of the summations are forbidden because they are affecting each other. So how exactly to solve it? Right? No, you can't. Because you still don't know what's going on. No. Because every I is represented by a specific choice of all the different K's. Each specific I here, okay, each specific I is a specific set of K1 and K2 and K3 up to Kn. Each specific I is a vector in this K space. Okay? This is a representation. So what do we do? This is what is called factorization. Factorization is basically saying, I know how to perform this sum in one single specific case. Only one. When all these different cases do not depend on each other. Okay? When E1, K1, or K1 doesn't care about K2, it doesn't care about K3, they don't care. All those indices can be whatever they like. Only in this case, I can actually solve this sum over here. Okay? And this is what we call factorization. This is the only trick I know. This is the only trick that anybody knows. Okay? To perform those summations, to actually know what is this partition function equals, and it appears only in the case when all the different indices or all the different energies of the particles are independent of each other. What is the case when all the different energies or all the particles are independent of each other? Ideal gas. Right? Very simple. This is the only thing that I know how to perform. Ideal gas. Factorization is bringing my system into representation of an ideal gas. Okay, so how exactly this factorization works? Yeah, question? Yeah. You need to make some transformation and represent everything in terms of ideal gas. Yes. Somehow. Everything that we know how to solve, what you know how to solve in classical mechanics. Oscillator harmonic free particles. What is Hamilton theory tells you? This is actually interesting. In analytical mechanics, what the theory of Hamilton tells us, that any system, by the use of these angle variables, remember? Yes? You can transform any system in a specific geometry to a system of harmonic oscillators and independent particles. This is the assumption that we are also using here. We are going to have systems with interactions, and we need somehow to do something to those systems to represent them in such a way that they will look to us as if they are ideal gas. Okay. Now, why it's called factorization? Let's look on this specific summation over here. So we can write it down. Questions?
I have a question.
Yes.
A few lessons ago, you told us that if I have two states with the same energy, we conclude this as one. So here, if I have two sets of K that equal to the same value, you said that every EI represented by
A specific K1, K2, K3,
yeah.
K4.
So if I have two sets of K that equal to the same value,
That means that I don't have all the states, yes. That simply means that I have a specific set of Ks, and this is my representation. But let me continue. Let's see what this mathematically means. Okay. So I want to write it down as K1, K2, and K3 e to the power minus beta epsilon 1 K1 multiplied by e to the minus beta epsilon 2 K2 plus epsilon 3 K3 plus epsilon 4 K4 plus etc. at epsilon n Kn. Okay. Now inside this summation, I'm changing the order of the summation. I'm saying let's leave this K2 and K3 and K4 outside. I will have e to the minus beta epsilon of I or j goes from epsilon epsilon j kj, right, multiplied by a sum, okay, as a sum of K1 e to the power minus beta epsilon 1 K1. Now what this guy is, it's thus a partition function of a single particle. Let's assume that I have a system that consists of only one particle. Those are the different energies. Ki's are the different K1s are the different states of my single particle. So this is simply a partition function of one single particle without any interactions. Okay. So I have a sum over K2, K3, K4 of e to the minus beta summation of j epsilon j kj multiplied by z1. This equals to partition function of one single particle. I can continue this process. I take z1 out of this sum, so z1 is out, and I have here a summation of K2, K3, K4 e to the power minus beta epsilon 2 K2 multiplied by e to the power minus beta, a summation of j goes from 3, here j goes from 2, j goes from 3, epsilon j kj. And I perform again the same trick. I can say, well, I can change the order of the summation and write it down as z1, a summation of k3, k4, etc. of e to the power minus beta, a summation j goes from 3 of epsilon j kj, a summation over k2 e to the power minus beta epsilon 2 k2. What is this guy?
The partition function of the second
Of the second particle. So this is z2. And what I left with? z1 multiplied over k3, k4, etc. e to the minus beta sum of j over 3 epsilon j kj. Okay? And this is z1 multiplied by z2 multiplied by this sum. k3, k4, etc., etc. e to the minus beta summation of j from 3 epsilon j kj. And I can continue this process on and on and on. Eventually what I'm getting to, z1 multiplied by z2 multiplied by z3 multiplied by z4 if they are equal, but they cannot, but sometimes they are not equal. So factorization means that I can represent the partition function of the whole system for the case when the particles are not interacting as a multiplication of the partition functions of single particles. Z equals to pi from 1 to n zi. This is what we call factorization. A multiplicative description of the partition function in terms of partition functions of single particles. What is the problem, physical problem with this representation? Not mathematical. I haven't done anything wrong mathematically. Physically, it's cumbersome. Why?
You assume an ideal gas?
Well, it's fine. I assumed that I can look on the partition function of a single particle. What is the temperature of single particles? Right? How do I develop the partition function formalism? I said, I have a macroscopical system. There is a heat bath. And this macroscopical is small, but it's large enough. It has some temperature. It's exchange energies, etc. It's doing something with the outside world. Okay, but it had to be what? Macroscopical. All this description, right? And eventually I am doing some mathematical tricks, and they say, well, forget about all this macroscopical stuff. You can treat each single particle, which is microscopical entity, not macroscopical, as if it has a partition function, as if it has probabilities. I don't really care. Okay? But this is true. Right? We haven't done anything wrong. We started with the system, and it is true only because I neglected all interactions between the different particles. And the claim of statistical physics is that for any system, but we don't know how to do it for any system, we somehow have to perform this factorization. This is the only true tool that we have. Okay? This is always our goal. When we look on the system and we want to understand something, well, it was the goal up to the 70s. Okay? When we look on the system, we need to perform some transformations and invent new representation of the particles such that beforehand they were interacting, afterward they were not interacting. Okay? By the way, if I have a partition function for a single particle, what is the probability, okay? What is the probability of my particle to be in state 3 or with energy? So what is the probability of a single particle to be in a specific state G with energy epsilon G, epsilon J. If I treat this mathematical formalism, it's exactly as the probability of a large system to be in state J with epsilon J. Exactly the same. F of J equals to 1 over Z. What is the probability of a particle, a single particle number K? Okay, so it's going to be Zk minus epsilon J multiplied by beta. I treat it as if it's a macroscopical system. The moment I can write a partition function, I treat all the different single particles as if they are macroscopical systems. I don't care. The math allows it to me. In order for eventually to describe all the system, I need to perform this multiplication. And this is fine. But I can go and treat each particle on its own, find out what are the partition functions of those different particles, and eventually multiply everything together. All right, let's see an example. So it's actually much more simpler than you think. the whole, eventually you need to remember or understand the technique. I need to separate the whole system into simple systems. I need to compute the partition functions of those simple systems, right? And that's it. And then I have to perform the multiplication. Yes. Yes, it's going to be to the power n. If the particles are identical, it's going to be to the power n. It's simple. Okay?
למה יש פה ZK ולא ZJ?
So this is the particle number K.
למה שם זה זה לא...
J, it's J, it's J. It's according to what I have written over here. Okay? Example. The two-state model. Remember the two-state model? There was some combinatorial problem. We have n particles. N particles. Non-interacting. Okay? And for each particle there are two states. 0 and epsilon. Okay? I want to compute something, right? Anything. I want to compute the pressure, I want to compute the energy, I want to compute something about the system. How do I do it? In microcanonical ensemble, I had to assume there is an energy and there is some combinatorial problem that I needed to solve, because I needed to count all the different states that fit exactly to my energy. What I'm doing here, I'm looking at this and saying, well, all the particles are exactly the same. Compute Z1. Okay. What is Z1? The partition function of one single particle. Remember, if they are not interacting, I'm looking on each particle separately, compute it, partition function, and then multiply. Okay. What is Z1? So Z1 equals to sum over I, e to the minus eta, epsilon I. Let's do it, EI. Okay. How many states a single particle can have? Two. Right? So we can have either enter this EI equals 0, so e to the minus beta multiplied by 0, plus e to the minus beta multiplied by epsilon. Okay, so Z1 equals to 1 plus e to the power minus beta epsilon. Z2 equals to 1 plus e to the minus beta epsilon. They are identical. Z3 equals 1 plus e to the power minus beta epsilon. Z equals par of j from 1 to n. Zj. It equals to 1 plus e to the power minus beta epsilon to the power, and we want to compute thermodynamical quantity. What is F? Minus 1 over beta log of Z equals to minus 1 minus K Boltzmann T log of 1 plus e to the minus beta epsilon to the power n. The free energy equals minus K Boltzmann T, a log of what? N 1 plus e to the minus beta epsilon. And we are done. That's it. Right? So much easier than computing exactly the states that fit to the total energy U that we have inside our system. You want to compute the energy? You can take either the derivative, right? You can take the derivative of this guy, or what else can you do? What is U?
Sum of FI.
Oh, I usually do not remember all those derivatives, right? I don't remember all those derivatives. I just simply sum, but it's a matter of choice. Okay? But usually I prefer to look on EI, e to the power of FI. Right? I can do this. Right? This is the general definition. Now, in our system, it's even simpler. The particles are what? They are not interacting. So I need to compute, right? So U, okay, is N multiplied by E1. Do you understand where I'm getting this formula from? What is U? Okay, so let's assume this is E1 plus the total energy, E, is E1 plus E2 plus E3 plus up to En. Okay. Now I compute the average. The average on the left hand side equals to the average on the right hand side. Their average, you're right. The average of the left hand side is simply U. Now the average of a sum is always a sum over averages. So we have a summation of I equals from 1 to N of EI, which is sum of I from N. Because all the particles are identical, this is simply the average of the first particle. Okay? And this is independent of index 1. So this is N multiplied by E1. And what is the average of E1, which is the average energy of single particle? We know how to compute it because we know the different energies of any different particle. Okay? If you prefer to take the derivatives and memorize those formulas, go ahead. I usually prefer to use probability theory. Okay, so what is E1? It is a 0, right? Because it has two states, either 0 or epsilon. So this is 0 multiplied by e to the minus beta multiplied by 0 divided by z1 plus epsilon multiplied by e to the power minus beta epsilon divided by z1. Okay, this is 0, this is left. So we have E1 equals to epsilon e to the minus beta epsilon divided by, what it was z1? 1 plus e to the minus beta epsilon, which is simply epsilon divided by e to the beta epsilon plus 1. Okay. So the average energy is N multiplied by epsilon divided to the e beta epsilon plus 1. That's all. Now, any system that we can separate into subsystems that are not interacting with each other, where additivity takes place, and we can perform this factorization like we did over here, solved exactly in the same manner. Okay? The problem is that most of the systems are not ideal gas. So we usually have to work extremely hard in order to make an ideal or factorization or ideal gas representation for those systems. Right. So that's all for today. There is a couple additional examples. We will see them next week. And good luck with the quiz on Tuesday. אני הולך, אין לי זמן היום לשאלות.
מה?
אין לי זמן.
אבל אתה נותן לנו ביום שלישי וגם אתה הולך היום, איך נשרוד?
תכתבי לי אימייל, אני אענה לך מדרום קוריאה. מה? אימיילים. אני אענה, אבל ביום שלישי אני אתחיל.